Engelhard Elementary. My name is Scientist Smith, and today we are going to explore the states of matter. Everybody say the word matter. Matter. I'm thinking that you said it. I hope you did. I am a chemist, and what chemists do is use the periodic table of elements to create everything around us that we see and some things that we don't see. Everybody say element, element. Some elements that we might be familiar with are hydrogen. You can say that word, hydrogen. Oxygen, which we all need to survive. We breathe that in every day. Breathe some oxygen in with me. Good, isn't it? Also carbon and gold and silver and platinum, aluminum, argon, krypton. I can go on and on. Today we are going to first start with solids. Everybody say solid, solid. So solids, all solids usually have a lot of molecules packed in really, really tight. That's how we can see them so well. Say molecule, molecule. So molecules are all atoms arranged. So if I take this right here, you can see that this is matter. This matter is a color, right? Y'all see that? It's also wiggly. Look at the wiggle, 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 wiggle. So this is what we like to call slime, or in science, we call it a polymer. Say that word, polymer. Polymer means many parts. So this has many parts to it. This started out as glue, just ordinary glue. Then I mixed in a little liquid starch. This starch has a chemical in it that makes this a little bit elastic. And it also stiffens up too if you add more of it. Over here, we also added a little bit of borax. This borax solution, when you put it in water, you wash off your glue and styrofoam mixture, and you get this. Then you wash it off with water, and this is a cool activity you can do at home with adult supervision, of course. So this polymer and this polymer I have on my wrist here also. Here's another type of polymer. Most polymers, as you can see, are plastics, and they have some type of bend to them. But all polymers don't bend. Some are a little bit more stiff and a little bit more rigid, such as this container here, and also this right here. This is really, really hard. See? Really, really stiff and more firm than the rest. But that's just all in how we create it and how we make it up. So I'll put this slime or polymer down, and we'll get on to another one that I really like, which is oobleck. Everybody say the word oobleck. Oobleck. So oobleck is a non-Newtonian fluid. Yeah, I know, that's a really big word, but you can try it. Non-Newtonian fluid. Again, non-Newtonian fluid. So that means that it's a solid and a liquid at the same time. How? Let me show you. So inside of here, I have some blue food coloring with some cornstarch and then some water. It's stiffened up already. I'll come around closer so you can see. You can see it's starting to stiffen up, right? So that looks like a solid. And even if I try to tilt it over, nothing's coming out. It's not even moving really. Pour a little bit of water in there. I can loosen up these solids, and these solids then become a little bit more relaxed. And when you add water to this mixture, you create what's called oobleck. Now, oobleck acts as a solid and a liquid, depending on how much liquid or how much solid you put in there. So right now, I have a handful. Now look at it. So with me adding water, you can see that it's starting to feel more and look more like a liquid, but it also has solid properties. Now, these solid properties exist when you have a lot of pushback. So if you see me, I'm pushing back, but right there it's a little splashing. But if I take a big clump, this chunk right here is really, really concentrated in solids. So there's more solids in there, and since there are more solids, sorry, I thought I saw something fly off my table. It's a little windy out here. So now you can see it's also liquid. Looks like a liquid as well. But if I push down on it right there, you can see and feel I can feel rather, it has a little pushback. This is also another experiment you can do at home in the safety of your home with adult supervision, of course. Use any types of food coloring. You can use different types different amounts of cornstarch so that you can have some oobleck that's a little bit more loose and wiggly like this, or have some that's a little bit more firm and stiff. This is a great physics experiment. Say physics, physics. Awesome sauce. Now we'll put that to the side. I'm a little wet here, so I'm gonna wash my hand off. As you can see, this will just wash right off. I'll show you. Just take it and just rub it. My hands are going to be a little stained with blue just for a little bit, but food coloring also washes off. I'll take my other hand just to make it a little bit uniform. There we go. Set that there. So solids. So we talked about solids, solid experiments that you can do at home, safe experiments. Let's get on to a little bit of liquid, a lot of liquid actually. So inside of here I have a snack for later. But now I'm going to take my gloves out of my styrofoam, which is also a solid, styrofoam. Nothing's inside. And what we're going to add inside of here is a liquid that I love the most. It's an element called nitrogen. Everybody say nitrogen! Nitrogen! Nitrogen is a periodic table element, and it's very, very dangerous if you are dealing with it as a liquid. So as a liquid, nitrogen is negative 321 degrees Fahrenheit. However, as a gas, we are breathing in nitrogen every day. Most of the air out here and even inside your house is nitrogen gas. About 78% of the air that we breathe is nitrogen gas. And it's also good for the earth and good for the ground if you are into gardening. So now I'll take this liquid nitrogen out of my dewar here. This is a dewar. Pour some in there. Now that we got a little weight, we can see that my styrofoam doesn't want to fly away. As you can see, now we see it a little smoking, right? This looks like it could be on fire, but it is not on fire at all. Actually, this is really, really cold now. All the air around us is getting cold, and you can see it just like clouds in the sky. I'll pour a little bit more in there and bring it a little closer to you so you can see just exactly what's going on inside of my container here. Now, look. Styrofoam is allowing my liquid just to settle in there and rest as a container in a vessel. Now I can take this balloon off and set it in there because we'll see what happens with these balloons. Take my gloves off for this because it's a little bit tough to blow up balloons with them on. Here's a pink balloon. And balloons are also polymers. With polymers, we think about elasticity. Say elasticity. Elasticity. How far something stretches, or the ability for something to stretch. Take another one. And there we go. And another one. And there we go. So I'm taking these balloons and putting them inside of my bin here, getting them nice and in contact with the liquid. So that liquid nitrogen, now I have to put on my gloves because it's not safe at all. That could burn me. So these cryo gloves are going to keep me safe. Now I'll pull out the first balloon that I had. Look at this balloon. Remember, it was the one I had on my wrist. And as you can see, it was really, really small. But as it warms up, look at it. As it warms up, it re-expanded. Put it right back on. Now, let's think about these other ones. Ooh, I have this one. So this balloon is actually a cool toy. See, I told you it was a little bit tough to tie the gloves on. Oh, got it. Oh, no, got it. Let's try it. Oh, there you go. I got it this time. There we go. Get in there. There we go. Boom. So this is a balloon that simply has a rubber band attached to it, and you play with it like that. See? Boop, 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 boop. This is a good hand-eye coordination or reflexes experiment for your little ones. See? And it's fun. You just bounce it around all day. Or if you like boxing, same thing. So let's get back to these balloons. Inside of here, I'll take this, put it in as well. I'll bring these a little closer so you can see what's going on. Look. So they're getting warm, and as they warm up, you can see, look, they start to take its shape. They take their shape back. Because what happens is when the gas molecules get cold, they get really, really close together because they want to warm themselves up. And then when they get out here in the heat outside of my styrofoam bin, once they get outside of my styrofoam bin, they then warm up, especially out here outside with the sun nice and hot and beaming on us. That's why it starts to expand so fast. But here's one right here. Look, flat as a pancake. And you can hear it. Listen to it. And as it starts to warm up, you can't hear that crinkly noise anymore because the actual rubber is now elastic opposed to being brittle. I'll show you. One that's brittle will crumble up. You hear that? So brittle. You hear that? Brittle. Again, if I did that, see, now I just took it out and it crumbled in my hand. See? Brittle. Pieces crumbled in my hand. This balloon now, look, it's elastic. But I cracked it because it was so cold. It was so brittle. And this balloon's too big, so it won't go down in there. But these, you can see there. Uh-oh, don't fly away on me. And look at this one. I'll take this one, and then this one really is cool because you can pinch it. And if you pinch it right there at a certain point, you can feel and see now it's starting to really decrease in size because the gas molecules are so cold, they want to warm themselves up. Gas molecules are pure vibrations. For instance, if I was to take, pop goes the balloon. This has air in it. This air is a type of gas. The type of gas is carbon dioxide. Say that with me. Carbon dioxide. Carbon dioxide is the gas that we breathe out. Breathe out some carbon dioxide. Feel it on your hand. Now, the harder you blow, the more force that you put towards the gas, and then you'll be able to feel it more. So if you blow soft, you wouldn't feel it as much. But if you blow hard, it comes out faster, right? We are systems, force. So this system right here, look, the gas had to go somewhere. You can't just stay in there unless you tie it. Unless you tie it just like I tied this one, the gas isn't going anywhere. So if I put it inside that cold liquid, put on my glove just like this one. Look, the gas didn't go anywhere. It looks like it, but in science, you could be deceived because, look, now it's starting to take shape and grow and grow, and the balloon's back to normal. Same with this one right here. Or I'll take this, set it over there so it doesn't fly away. Give it a nice brace. This one, let me get the one, you gotta push it down inside the liquid, because if it's not touching the liquid, then it's not really getting cold. This yellow one, it got cold, as you can see, and as it grows and grows and grows. I'll put one in the palm of my hand and show you exactly how much force this gas actually can push back. So look. So as it warms up, you can see now it's even starting to push my hand away. But my gloves are meant to keep my hand safe. So it's keeping it's also keeping the balloon cold on that side. It's insulating it. But as you can see, look, back to normal. Balloon. Uh-oh, missed it. All right. The toy balloon. So this one, look, this one's brittle. So as it warms up, now we can play with it. And it'll start to grow back to its normal size. Awesome. So we'll stick this right here so it doesn't fly away. All right. Now, remember, this was liquid nitrogen that was actually making things cold. Now, liquid nitrogen is very, very subtle when it comes to seeing it. It looks like it could be water. That's one thing in science. You never trust what you see with your naked eye. Look, that could be water. So you never eat or drink when you're doing science experiments because this can be mistaken for some soda that is really, really hot or really, really cold, or some water. Look, just clear, colorless liquid. I'll bring it closer so you can see. These two liquids are practically the same. This one just has bubbles. Bubbles meaning this is starting to evaporate. Say the word evaporate with me. Evaporate! So evaporation means that this is turning into a vapor. So this liquid is turning into smaller and smaller molecules of nitrogen. Nitrogen, the letter N. Nitrogen is starting to expand. So as it expands, it starts to grow and grow, warming up back into its natural state. This liquid doesn't want to be a liquid at all. It would rather be a gas molecule. That's its natural state. And look, it's making snow on my hand because there's water molecules all around us. We can't see them. They're zipping by this camera as we speak, or as I speak, and there's some accumulating on this. This right here is called condensation. Say that with me. Condensation. So whenever you see something accumulating on glass in a cold weather situation, or even in the inside of the freezer, that's condensation. So water condenses onto this plastic, and then as you can see, I can wipe it off right there. But this will eventually warm up and we wouldn't be able to see it because it'll be a clear, colorless liquid. So this liquid, I'll pour it out so you can see it. Now, I want to take that liquid and put it in this. Listen to it. So as you hear it, it's starting to boil and fizzle, and I try to trap it, and look, it tries to push off this top because look, shake it, boop. Inside, that liquid is expanding and growing, getting bigger, and as it gets bigger, it starts to accumulate space, and that space is too small for the big gas molecules to actually expand and grow out, and this top is easily popped off, as you can see, and here. And this will keep on going on and on until all of the nitrogen is gone. See? It's going to keep popping. Pop. It's like it's talking. Pop, 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 pop. And as I shake it, I'm shaking it because I want to agitate it and make sure that I force it up, because the more I shake it, the more energy I give it. The more energy you put into a system, the more energy that system will have. And a lot of times what goes in has to come out of systems. And that nitrogen doesn't want to stay in there at all. It would rather be out. Opposed to some system that is really, really what we call stable. This is a stable environment for this liquid. And this is glue. So this glue is not creating any type of gas bubbles, and it's nice and cool inside of its container. And other solids do the same thing as well. But gas molecules, they are very, very hyper and energetic, as we saw with the balloon. See? Those gas molecules inside that balloon did not want to stay in there. They would rather bounce around and move around. Oh, look, solid. Look, we made snow again. Condensation. It started to accumulate. Even in this hot sun, you can see it's starting to still smoke or steam. This is just cold vapor. A lot of times we see that cold vapor in the wintertime, early in the morning, or even during the afternoon when you go and you see your breath in the winter. That's because your hot breath is getting into a cold environment. And when that happens, the molecules condense into clouds. No clouds behind me, but there's one over there and one over there. All right, so that's one thing. Let's move on to another liquid. So a liquid that you all have at home. I'll take this and chuck it over there. Liquids that you all have at home. Vinegar. Vinegar. So vinegar, another clear, colorless liquid that we could easily mistake for something very dangerous, such as hydrogen peroxide or rubbing alcohol. So again, that's why we do not eat or drink in science. When we're doing experiments, it's not a good thing. So I'll take these off for now. We'll get back to this a little later. Set that to the side. And we'll bring out the vinegar. So here we have our vinegar. Boom, vinegar. And empty bottle. This is an experiment that you can do at home. It's just like the old volcano and today balloon in a bottle experiment. So what you need is vinegar. You can have white vinegar or apple cider vinegar, either or. Just some regular ordinary baking soda or baking soda or baking powder, either one. This is a spoon just to take and use for my baking soda. This balloon you want to stretch open. Stretch it open because remember it's elastic, so it stretches. So I'll show you a little bit closer. So this elasticity, it stretches. Remember, elasticity, something that's ability to stretch. Elastic. That is elastic. Now, what you want to do is open this up, take some baking soda, and pour it into there. Pour it out here over the grass so I don't get it on the table. All right, so this is an acid-base reaction. This right here in our balloon is our base. Today our base is sodium bicarbonate, also known as baking soda. Say that with me, sodium bicarbonate. Again, sodium bicarbonate. Awesome sauce. Now, we'll take this. Also, you can use food coloring for this as well. I chose yellow. And I chose to use a separate container so that I wouldn't have to pour all of my food coloring into this or pour from this into my small little bitty spout here. I have a container that has a spout there to make it easy to pour from. So then you take your vinegar and pour in just like that. Another quick fun tip when you're dealing with vinegar or different liquids that smell very, very strong, you never want to smell them directly. We bring the smell to us with a technique that's called wafting. Wafting in the air. Say that word, wafting. So it's like bringing the molecules to you. The aromatic rings, bring them to you. Aromatic, another chemistry word, aromatherapy, aromatic. A lot of us are doing some aromatherapy now, smelling some eucalyptus oil, some frankincense, some lemon, some lemongrass, all types, some orange zest. Now what we're going to do is take our clear bottle, clean, empty bottle, and just transfer the vinegar into it like so. And you can smell the vinegar. It's really, really strong smell as you pour it out. This vinegar also has another name for it called acetic acid. You can try to say that word with me, acetic acid. I'll show you. Come a little closer for this one. See? Now inside we just have our vinegar. That color is weird, so I'm gonna take a little green. Let's go green. How about that? Let's go green. Ooh, that looks much better, huh? Yeah, I think I like that. So now we'll take this, and next we want to take our two containers here. One container filled with our base, our sodium bicarbonate, and our other container filled with our acid, our acetic acid, or also vinegar and baking soda. What you do is take this, remember it stretches and is elastic. So you take it and you snap it right over the top of the bottle. See? Snap it right there, and you can see that the solids are still hanging over the side, just like that. And this, you want to make sure it's nice and tight up underneath, see? So I can just even hold it like that, pinching, making sure our solids stay put. This is going to create some more gas. A lot of us are familiar with gas bubbles being in our sodas. That gas is also carbon dioxide gas. Carbon dioxide, we heard that before. We blow it out all the time. We drink it in our carbonated beverages as well. Now, this is just an invert reaction. You take this, pour it over, and then down come the solids. Once those solids react with this liquid, it creates that gas. Those gas bubbles then will have to go somewhere, right? They have to go somewhere. And right now, we have a closed container. This has no leakage. This has no leakage, and this has no leakage. So what's inside is going to be there, and what's inside was already there. You ready? Here we go. In 3, 2, 1. And you see, already, instantly, all of that is now inflating the balloon. And it's starting to create even more liquid. Is starting to bubble up and foam inside of the balloon, as you can see. Look at that. Looks like it's a big bubble bath inside of our bottle. Now, all of those bubbles have popped, right? So we had bubbles in our liquid. Now, as those bubbles pop, those bubbles were filled with carbon dioxide gas. That gas still exists, and it's inside of this balloon. That's how our balloon is inflated, just like that. See? And you can see now there are more bubbles starting to pop. And now it really looks like some soda. And I'll shake it a little bit more. See? Very cool reaction. Make sure you fill the balloon so that you can see and feel when you're doing your reactions. Because remember, this balloon was not inflated when we first started. And all we had was a solid and a liquid. On to the next. So this I'll set in here so we can have a visual so that we remember it. Next, we're going to go to a great experiment that I love. It's called elephant's toothpaste. Elephant's toothpaste. All right. So elephant's toothpaste is a mixture of liquids reacting together to create a big foam that usually looks like toothpaste, and it gets so big that elephants could use it to brush their teeth if they brush their teeth. Now, we'll take this, put these to the side, so I don't want to get those messed up. Next, we want to pull out our Dawn dish detergent, and this is a solution called hydrogen peroxide. So inside of here, there's hydrogen peroxide and water. Take out potassium permanganate. This is going to be our catalyst of our experiment. Now, hydrogen peroxide, when we have it as is, it already goes through a process called decomposition, or decomposing, or decaying, or breaking down. Say that word. Decompose. 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 Awesome. So this is breaking down into hydrogen peroxide and oxygen gas. Remember, oxygen gas, we breathe that in every day. About 20%, 18 to 20% of the air out here is oxygen gas. And the trees, they give us oxygen gas in order to breathe. And we give them carbon dioxide in order for them to breathe. You're welcome. Now, we'll take this, and what we want to do is mix two different solutions together. First, we're going to take some water, and I have my water here, our water, and today we're going to make this yellow. Let's do yellow. Yellow. We'll do yellow with this because this potassium permanganate is a purple color. Purple, 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 purple. Now, we'll take the potassium permanganate, and we want to pour it into that right there, like so. Nice purple crystals. I'll bring it closer so you can see. It gets really better once I add the yellow, the water. See? Purple crystals. As you can see, nice purple crystals. I'll pour the water in and you can see better. And goes our water. And I added yellow just to brighten up this purple because it's really, really dark purple. So I spread it around. So inside of here we have our potassium permanganate, which is our catalyst. And we also have our water. So this is our water solution in our potassium permanganate solution. Potassium permanganate solution, excuse me. And I'll swirl it around. Ooh, look at that. This flask is called an Erlenmeyer flask. So an Erlenmeyer flask actually, as you can see, has a different shape. And it's easy for you to mix solutions up, just like so. So you don't have it spilling or splattering around with a smaller opening. Now, we need soap. Because, remember, we're going to want to trap these oxygen gas bubbles. Oxygen gas bubbles, remember, just like our container here, these bubbles are carbon dioxide gas bubbles. So different types of gases can be in any type of bubble. This right here is going to create some oxygen gas bubbles. Oxygen gas bubbles. So here, I'll take some soap, put our soap in there. Also, we want to put our soap into our other solution with our hydrogen peroxide just to make sure that we get as much bubbles trapped as possible. And again, you can swirl this around. You can try this at home using yeast, warm water, some yeast, warm water, a balloon, and a container just like this as well, mixed with 3% peroxide. You can also look this up on YouTube or Google. This is called an exothermic reaction. Exothermic. So we're escaping something. Something's escaping. What's going to react here is going to be so powerful, it's going to create heat. That's why we call it exothermic reaction. They heat up very, very fast, and this is going to create a big foam. I'll pull these over to the right and to the left so that we can see this a little bit more clearly. Safety first, always safe science. Remember to always be safe when doing science. So now we have our solution of hydrogen peroxide and soap. Dish soap, any type of dish soap. And I'll take this and pour it into this like this. All right, you all ready? Here we go. This one I'll bring a little closer so you can see it. Here we go. All right. Center that a little bit better. And let's start at 5. In 5, 4, 3, 2, 1. Look at it. It's still foaming. And it's a nice color there. As you can see, the purple, and it's plopping all over the place. It went really fast because this was ready to react with our catalyst in there. As you can see, our catalyst still has specks of purple in there. And look, it's kind of like elephant's toothpaste, right? Elephant's toothpaste, a very fast reaction. Now, we'll take this here. This is one of my I love this reaction because it actually gets you to see what's going on with liquid nitrogen as it expands, what it also does to different types of materials, more importantly, water. What we're going to do today is expand this liquid nitrogen a little bit more faster, just like we created our experiment last time. We had a catalyst to speed up a reaction. This catalyst is going to be water today. So we have our water, and this nitrogen is already starting to expand and grow back into its natural state, which is a gas. Now, as I blow into that, the heat from my breath is reacting with it, pushing it down. Pushing back is cold air and different types of gases that are also in the air around us, condense into gases that you can see, just like clouds in the sky. Now, what we want to do, I'll take this and I'll pour from here. we want to add some water into my container here. This one is going to be the cold one. So I'm going to do a cold one, and then I'm going to do a hot one. We'll see the difference of how molecules work when they're cold and then when they're warm. Take these off to be a little bit more comfortable. Now, pour a little bit more water in there. Let's just pour the rest. There we go. This is also another big cloud that we're going to create. But remember, this is going to be a cold cloud. Since it's a cold cloud, we have to realize that it's going to be really condensed and thick in structure and shape and size. Safe science, so I'm going to put on my gloves here, my cryo gloves, my handy cryo gloves. This one can fly away, but it can't go. Now, alright, here we go. You ready? I'm going to just do a direct dump, as everything starts to fly away. Alright, here we go. In 5, 4, 3, 2, 1. Look at it. Look, so this is all cold air, and it's going with the wind. So that water in there is starting to react with our cold liquid nitrogen, and it's freezing. So you can hear it freezing, right? Now, I'll take my hands in here, and look. So now, I'll take my hands and pull out some ice. Look at that. Ice. So the water that we put in there turned into this. Looks like glaciers, right? Look at that. No, my hands. Don't worry about my hands. That'll wipe right off. Got some acetone. Clean that right up. But look. Ice. Looks like ice cubes. But remember, in science, we do not eat or drink science. Even though this does look like edible ice. When you're creating a project, things look like they can be edible. You put food coloring in the right type of liquid, it could be your favorite juice any day of the week. So really important. We practice safe science and always have supervision of an adult when deciding to do an experiment. And also, do not eat or drink when doing your experiments. Let's move to another location for the last experiment. So, all right. Hello, Engelhard Elementary. Liquid nitrogen is now going into our bucket here, and we're going to evaporate that again. Remember, we're going to speed up this reaction. Today we have hot water. Earlier we used cold water to speed up the reaction of evaporation. Instead of cold water, we're going to use hot water. And as you can see, this has already begun to evaporate. But this hot water is going to make it expand even further, and big cloud is going to erupt out of there. All right, safe science, everyone. You all ready? Hey, y'all. How's some more people watching? Here we go. In 5, 4, 3, 2, 1.